So your whole math career, can you see this coordinate axes here?
Yep. Yep.
So your whole math career, we've been living here in terms of graphing, right? X or horizontal axis, Y or vertical axis. So polar coordinates is a totally different way to locate points in the plane and then therefore graph sets of points. Okay. So let's talk about how that works. So this graph paper that I made available to you, it's in modules. Also, there's a link on the announcement that I posted. If you weren't able to print it out today, that's okay. You can do hand sketches today, but then it's going to be really helpful if you have, 3-4 sheets of this polar graph paper on hand. And it looks like it's a sheet of paper with a bunch of these on it. So if you don't have it today, you can make your sketches by hand, but definitely it's going to be really helpful to print out. I think like each page has like 6 of these, and then so you can use them for, like I said, for plotting points and practicing plotting graphs, and it's just going to be really helpful to not have to draw this bullseye every time. So print out a bunch of those copies, and then always have those at lecture, and they're going to be really helpful for doing your homework as well. Okay, so here, this is what we call the polar plane, and this point is called the pole. Okay, right at the center. So we used to, and that was in rectangular coordinates, that was called the origin, and so now this is called the pole, and and so how it works is there's 2 coordinates, and so we write coordinate pairs as r theta. And r is the distance from the pole. Theta is the standard trig angle. I think I have this, let me see, I have the explanation of this here down here. Yeah, so let's just, so polar coordinates are based on the distance from the pole, r, as a function of the angle theta. The standard angle swept counterclockwise from the positive x-axis. Okay, so but here's the thing to watch out for. When we list ordered pairs in polar coordinates, we put r first, and then the angle second. So when you see them listed, they'll be listed that way. But really, that's backwards from how we think. Okay, when you think about plotting points and plotting graphs in polar coordinates, the angle comes first. Angle comes first. So let's see that. So here's our standard trig angle, swept counterclockwise from the positive x-axis. This is how we define sine and cosine and all the trig functions. So it's the angle swept counterclockwise from the positive x-axis. So these are positive angles. So you also, what is a negative angle? That would be sweeping clockwise. So these angles would have a negative measure, a measure less than 0. For instance, this is the angle negative 2.41. Okay, here's the angle measure positive 3.93. Okay, and so let's just come here to say 2.1 here, 2.19. Man. .25, beautiful. Okay, so here is the angle measure 2.25, and then once you've picked your angle measure, then R is along that trajectory at the terminal side of the angle, right? So initial side of the angle is the positive x-axis. The terminal side of the angle is here, and this is the angle measure 2.25 radians. And once we've established that 2.25 radians, then from there, along that trajectory on the terminal side, we have values of r. So now this is now the distance from the pole, r, in the direction of 2.25 radians. So what are the coordinates of this point right here? What are the coordinates of, so a coordinate system is for locating points in the plane, right? A coordinate system, a two-dimensional coordinate system locates points in the plane. So this point right here would be have what coordinates?
3.5, 2.25.
Okay, someone said 3.5, 2.25. That's right. We put r first, but really, I'm going to write, we think angle first. So I'm going to think, first I'm going to sweep an angle of 2.25 radians. And then once I've established that trajectory, now along that ray, that terminal ray, we're going to go out, say, from the origin, or sorry, from the pole, 3.5 units. So that's the point 3.5, comma 2.25. Okay, so why they list r for, I don't know how it came to list r first and then theta, but that's the convention. That's how textbooks do it. That's how you'll see it online in the homework. So we will stick with that. But just remember that even though the points are listed as r theta, we think theta first, establish that direction from the pole, and then along that direction, our distance is r. Okay, so let's just, what does the number 2.25 mean? So let's just do a little quick review of radian measure, or maybe some of you have really never learned that explicitly. So this angle measure of 2.25, what does that number mean, 2.25? Anybody know?
2.25 radius lengths.
Okay, what is 2.25 radius lengths?
I'm not too sure.
Yeah, so it is right. It's actually a distance. It comes from a distance measure. This comes from 2.25 radius lengths. But where? How? 2.25 radius lengths.
Circle.
Yeah. So if my radius is 3.5, so here's my radius right here of 3.5 from the pole, right? If I take that radius of 3.5 and I start wrapping it on the circle with radius 3.5, okay, my first time, so the first radius length, so this is one radius length from here to here. And then I do that again, starting from here, I wrap another radius on here. And that would be another radius length. So to here, this point is two radius lengths from the positive x-axis wrapped on the circle of the radius that I have. So this is one radius length, this is a second radius length, and then this is a quarter radius length from here to here. So that's why, so along the circle of radius 3.5, if I wrap radius lengths of 3.5, 2.25 of those will take me to here, and so that's why that's the angle measure 2.25 radians of openness. But now that would be the same on any circle. So if I came in here and did the circle of radius 1, well, one radius length of that circle would be this far. Same angle measure, 1 radian. 2 radius lengths would take me this far. So that's 2 radians, and then a quarter of a radius length there. So no matter what radius you pick, lying that radius along the circle will be the same amount of openness, right? So 1 radian, 2 radian, 2.25 radians along the circle of radius 1, or a circle radius 2, a circle radius 10. Okay, so this proportionality, right? So the distance along the arc is proportional to the radius. So that's what 2.25 radius lengths means. It says pick any circle, take its radius, lie 2.25 radii along that circle, and it'll take you this far around the circle, and that's the angle measure 2.25. Okay, so now we've established that this is the direction of r in the direction of 2.25 radians. What about negative r then? So if I establish this as 2.25 is my trajectory for my r axis here, where would points that have a negative r value be?
In clockwise fashion.
No, so we're not gonna. The angle is established. I'm not gonna change the direction of the angle. I'm gonna keep my angle as 2.25 is going this way. Now, what's a negative r for this angle 2.25?
Would it go on the other side of the pole relative to the distance?
Yeah. So what quadrant is that?
Fourth for this one?
Yeah. So if your angle say is 2.25 radians, then a negative r value would be in the opposite direction as the angle, the direction for positive r values, which is along the ray, the terminal ray of 2.25. So negative r goes this way. So what is this point right here? Let's say this point. What are the coordinates of that point?
-4, 2.25.
-4 and positive 2.25. So the positive, so that the angle, we sweep the angle of 2.25 radians, it points us this way. That's the positive, that's for positive r values from the pole. Negative r values will go in exactly the opposite direction as the direction of the terminal ray of the angle. And we will practice that. We will definitely practice that. Okay, so let me clear my drawings here. So what about standard angles? All right. Okay. So we said we went around 2.25 radians. So I'll go around. I'll go around this circle. So 1 radius length is about there. 2 radius lengths is about there. 3 radius lengths doesn't quite make it halfway around the circle. That's 3. So this is 1 radian, 2 radian measure of angle. This is 3. So how many radius lengths or how many radians does it take to get exactly halfway around the circle?
Pi.
Yeah, right. So pi is the number 3.14159, and this is an irrational number. It's a repeating decimal, it's an infinite non-repeating decimal. And so pi is the number of radius lengths it takes to get exactly halfway around the circle. The things they never told you, right? Maybe some people are hearing that for the first time. So if you take a circle and take its radius and wrap it around the circle, it'll take pi of those to get exactly halfway around. And so then that forms the basis for kind of our symmetric key angles in the circle. So a quarter of a circle will be what angle measure?
Pi halves.
pi/2. And then half of that splits the first quadrant in half. pi over 4.
By 4.
And then halfway through the second quadrant will be 3 pi over 4. And so at some point in your trig pre-calculus, you learned these angles. So this one's pi over 6. This one's pi over 3. So pi over 6 then would be splitting the first quadrant into thirds, right? If you take pi over 2 and split it into thirds, then that's going to be pi over 6 and pi over 3. And then you could do the same thing in the second. You get 2 pi over 3 here. And then 5 pi over 6, splitting up the second quadrant into thirds. I'm also showing the twelfths here. This is pi over 12. This is 5 pi over 12. No. 1, 2, 3, 4. Yeah, 5 pi over 12. 6, 7 pi over 12. 11 pi over 12, but those are less common. Okay, but so what I want to emphasize though is that these angles are familiar because they're based on symmetry in the circle. But these symbols, these are not just labels for points on the circle. These are numbers. So for example, what is the number pi over 6? What is that number? That's a number. What value is it? It's close to what?
1/2. A little over 1/2.
Yeah, a little over 1/2. So let's get it. Let's get a little more better approximation than that. So pi over 6, 0.523. So what does that number mean? 0.523. So pi over 6 is a number. It's not just a label for a spot. It's a number that means 0.523. And 0.523 what? What does that number represent?
About half the radius.
Right, so it means that this arc length to get to that terminal side, here's the terminal side for pi over 6, it means that this arc length right there, to get to that terminal side pi over 6, is this fraction of a radius. It's a little bit more than half a radius. So these symbols, 5 pi over 6, 2 pi over 3, again, they're not just labels for places. They are numbers that mean how many radius lengths it takes you to get to that. If you went that many radius lengths, then that would represent that angle of openness. So for instance, what's the number 5 pi over 6? It's 5 pi over 6. 2.618, which means what?
The length of the arc length drawn by that is 2.61 times the radius of the circle.
Right. So going to this point on the, so that right there is 2.618 radius length. That arc length is 2.61 radius lengths for whatever circle I choose. And it defines an angle, right? It defines a terminal side of a ray from the positive x-axis to give you that angle. Okay, so if you don't remember, these key symmetric angles in the circle, there's 16 of them. So be a good time in the next day before class on Wednesday to brush up on those, because that'll be helpful. Okay, I can barely hear you. Is there someone asking a question?
Yeah, do you also want us to know them in radians?
I didn't understand.
Do you also want us to know them in radians?
These are radians.
Okay.
Yeah, it's just with a pi in it. It's a multiple of pi, which is halfway around the circle. But these are all radian measures.
Oh yeah, sorry, thank you.
Yeah, sure. Okay. So what's next? My printer didn't work this morning, so I have to see here. Key angles, plotting points. Okay, so we got to practice plotting points. Super important. So I have a bunch of, if you have your graph paper or you want to make sketches, I have a bunch of practice points here. Plot each point in the plane. So I'm going to give you 5 minutes to work on plotting these points and see how you do. So remember, a negative r value means in directly the opposite value, the opposite direction. I'm going to turn this off here. So a negative r value means go in the opposite direction, like the red direction. So here's the angle 3.96. 3.96 radians takes you along this axis here for values of r. So the negative r values would be exactly in the opposite direction, back in the first quadrant. Okay, that's negative r values. Negative theta values, so here's 0. There's 0. Negative theta values go in the clockwise direction from the x-axis to define positive r. So here's a negative angle of 1.97 radians. And so then positive values of r will take you here in the third quadrant for the angle measure, negative 1.97. All right, so try 5 minutes. Try plotting these points. And see how it goes, because we really want to think about, really be good at this, understanding the coordinates, right? And so remember, always you're going to do the angle measure first and then radius, but as they're written, radius comes first. Okay, so go work on these, and then as you're working on these, I can take a question or two. Does anybody have a question right now? Okay, so regroup at 10:10. See how you do, okay? And really really work on this. Certainly this is part of the quiz today, but really work hard on this. Don't just turn the computer off and do something else. And then as you have questions, I'll be listening for questions. You can just speak them out.
So with the radian measure, is like the arc length, or is it the radius length?
It's the arc length measured in the radius length. So you're measuring an arc around the circle using radius lengths. So
Okay.
I don't know. Does that help?
Yes.
So I'll kind of do another example here. So here's 1.3 radians. That means on any circle you pick, say just pick this circle right here, this is your radius length. It's going to take 1.3 of those to get to that ray along the arc. So if this is one radius length, then this, if you do 1.3 radius lengths along the arc, defines the angle measure of 1.3 radians. Does that clear it up?
So the 1.3 radians is like the arc length?
Yeah, so really radians, then it's the same value. So radius length is a distance along the arc, and radians is a measure of the openness corresponding to that same value of radius length along the arc.
Okay, I get it. Thank you so much.
Yeah, so radians is not a distance, it's an openness that's the value of which is determined by a distance along the arc.
Professor Ashford,
Yeah.
got a good question in the chat if you want to
Sure.
answer it. It's from Lauren Thornton's guess, can we technically write all the radii as positive, but with a different angle that
Yes.
means the same thing?
Yeah, we're going to talk about that. That there's, in polar coordinates, given a location, there are many ways to write the same location. So yes, but that doesn't that doesn't mean you can just always brush off negative values. You need to know your negative r values, how that works. But yes, you can rewrite any point in multiple ways. Okay, let's get started. So here's the angle measure pi for this first example. Angle measure pi. So that takes us pointing straight to the left, and then we're going to go positive 1 r straight to the left. Questions on that one? Right there. That's 1 comma pi. Point A. So I'm just going to fly through these, and you can stop me. Okay, next, angle measure of negative 2 pi over 3. So that's going to be back this way. That's going to be actually right there. Oh, almost had it. Right there. Ah. There we go. So this is the angle measure negative 2 pi over 3. It goes clockwise from the positive x-axis, and then we'll go a distance of positive 2 along that ray. Here's the point for question B. Questions on that one? Okay. And now we're going to go positive. Now my angle is positive 3 pi over 4. That's in the second quadrant. Right there. There's positive 3 pi over 4. And then, so this would be, our values would go this way if r was positive along that ray for 3 pi over 4. So negative r values would go this way. So negative 3 would be right here. So this is for an angle of positive 3 pi over 4 with a negative r down here in the fourth quadrant. Okay, pi over 3. So pi over 3 is right about there. Getting better with my finger here. All right, so there's pi over 3. And then in that direction, 2.5. This point right here. Are we good? Go ahead and shout out your questions if you want. All right, so now 7 pi over 4, what quadrant is that in? So there's 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 is about there, 6 pi over 4, 7 pi over 4. Seven pi over 4 is that direction. And so here we are at 7 pi over 4. So our values point down here in the fourth quadrant. Negative 4 then would take me the opposite direction. Up here. There's the point 7 pi over 4 for theta and negative 4 for r. Okay, finally, negative 5 pi over 6. So that's almost halfway around, right? Pi is exactly halfway around. So going in the negative direction means going clockwise, like this. 5 pi over 6 is, had it. Close enough? Okay, so there's negative 5 pi over 6. It's like almost halfway around. And so then r value would be pointing the direction of negative 5 pi over 6 would be this way. So negative 2 would then put us back in the first quadrant. So there's F. Okay, questions on plotting these 6 points? Any questions on those? So again, this was A. This was B. This was C. This was D. This was E. And this was F. Okay,
Wait, I
so
have a question.
please, please.
So I was plotting these by just measuring out the radius distance first and then doing the angle. Is there a particular reason why you're teaching us to do it the other?
Because when you do functions, r is a function of theta. So we're going to be plotting functions, and r is a function of theta. So you
I'm
can't.
not sure I understand.
Does that answer it?
No, I don't really see how that connects.
So like your function is y equals x squared. Do you pick y values and then get the associated x values when you do this? When you plot a point, say.
Oh, okay. So
So how do you plot points? You pick x first, and then you get the associated y, and that's how you would do this. We let x vary, right? We let x vary, and then we see y values varying with x.
okay, so theta is like it's gonna be our input.
Yeah, exactly. Yeah. So theta is the independent variable in these functions. For every theta, the function generates an r.
Okay.
So we're going to think about theta varying through angle measures, and then what's the corresponding r that we get. And if you try to do it the other way, forget it. Because there could be many, many angle measures that end up with the same r. And so if you pick an r first, you could get a whole bunch of angle measures that have that r. And then how would you graph that? Does that answer it?
Yeah, I guess only right now is the time that I could do it in the other order. It seems weird.
Yeah,
that
when
they
you
would
plot
put
a single point, it's fine. It's fine to do that. You can do that, but just to get used to the thinking, I'm trying to teach you to think in polar coordinates, which you'll have to do when we're graphing the curves. You have to think theta first and then r. Okay, other questions? All right, so then someone pointed out the issue during the break or during our breakout time that there's more than one way to write a point. So let's look at point D here, 2.5 pi over 3. What's another way to get that location besides 2.5 pi over 3?
Negative 2.5, negative 2 pi over 3.
Okay, all right, so you suggest what angle?
Negative 2 pi thirds.
Negative 2 pi thirds. Okay, so let's start at 0. Here's 0. So we're going to go, he wants to go negative 2 pi thirds. Like that. So negative 2 pi thirds takes us in this direction, and then go negative, what? Negative 2.5. Does it work?
Yeah. But
Yeah, that works, right? So we got 2.5, our base point, so our original location we plotted this way. But if you went negative 2 pi over 3, which is directly across from pi over 3, and then went negative 2.5, you get that same point. Okay, someone else has another way to write it. What's another way to write that location for point that we get in part D?
Did you say 2.5 comma 7 pi thirds?
Okay, so there's another, let's see. Is there another positive angle? So you want a positive 7 pi thirds?
Yeah.
All right, so good. So yeah, so we could go all the way around once, which would be 6 pi over 3 or 2 pi, and then you could keep rotating another pi over 3. So exactly, so that would be another pi over 3 from 2 pi would be 7 pi over 3. And then you go positive 2.5. Good. Another way.
you do negative 5 pi over 3 or 2.5 negative 5 pi over 3?
Okay, so let's do a negative angle that takes us all the way to that radial line. So here we go. We're going to go a negative angle. We're going to go through the fourth quadrant first, and then third, second, and so now we'll have a positive r in that direction. So what is that angle?
I think negative 5 pi over 3.
I think you're right. So let's just count it out. There's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. That's it. So it's negative 5 pi over 3. And that would be positive 2.5. Okay, is there one more that anybody sees?
Negative 2.5 and 4 pi over 3.
All right, here we go. Let's try that. So you want, what angle measure did you want?
4 pi over 3.
4 pi over 3. Okay, so, all right, so yeah, so let's send our angle measure. Let's get the positive angle measure that takes us down here. The positive angle measure that takes us here, and then take the opposite of r, our negative r value. So we want to come around here, positive theta into the third quadrant. And tell me again what that angle is?
4 pi over 3.
4 pi over 3. It's one more third than 3 pi over 3, which is halfway around. And then in the direction 4 pi over 3, we can go in the negative r direction. So all these, look at 1, 2, 3, 4, 5, 6, and we could write more. We just wrote 6 ordered pairs that gave us the exact same location. So this is a difference between rectangular coordinates and polar coordinates. In rectangular coordinates, if you have a location, there's only one ordered pair that gets that location. All right? If you have polar coordinates and you have a location, there are multiple, in fact, an infinite number of ordered pairs you could write to pinpoint that location. Okay, so now let's superimpose the xy plane onto the polar plane here. So I'm going to turn on the axes. So now we're going to look at kind of both planes, the rectangular coordinates and the polar plane together, and ask, what are the x and y coordinates of that point? What are the x and y coordinates of the point? Could I get it? So these are all polar coordinates for that location, but there's going to be one set of x and y, one pair, x and y, that's going to get me that location. There's not going to be multiple. And so what is it? So here's my x, here's my y. So what does x equal, and what does y equal?
But would x be the 2.5 that we chose, but then y is the sine of the angle that we have that brought us to that point?
Not quite.
Would it be the radius times cosine of the angle for x and the radius times the sine of the angle for y?
There you go. Okay, so you remember your trig. There we go. So if you remember your trig, this distance, so we have like a triangle, right? We have a right triangle, and the hypotenuse is the same as our r value, right? The hypotenuse is r. That's the distance from the pole. So in this case, r is 2.5, and then we have this angle theta, and so we're talking about a trig triangle here. So x is r times cosine theta, and y is r times sine theta. Back from your pre-calculus. So let's, for this particular point, so that's always true. And then what's a relationship that brings together x and y and r? So say we had x and y and we wanted r. How could we do that?
Pythagorean theorem?
Yeah, this is the Pythagorean theorem, right? R is the hypotenuse. The x and y coordinates are the lengths of the legs. So it'd be r squared equals x squared plus y squared. So now we're talking about transitioning, converting between polar coordinates and rectangular coordinates. So this particular point would have coordinates, what, 2.5 cosine pi over 3, 2.5 sine pi over 3. And cosine pi over 3, I think that's a half. Is that a half? Yep, it's a half. So it'd be 1.25. And this is radical 3 over 2. So it'd be 1.25 times radical 3. And that's the only way in rectangular coordinates that you could write the location of that point. There's no option here. There's only one horizontal distance that point is, and only one vertical distance that point is. But in polar coordinates, because we have negative r values and we can rotate in the negative theta values less than 0, there's multiple ways to write the same point. In fact, we found all these ways to write that point right there.